Hello and thank you for joining us. Welcome to this webinar event. This is one of many such webinar-based professional development events brought to you by Texas Instruments Australia as part of our ongoing support for teachers in the classroom. Today's topic, transformations. And your presenter, Peter Fox. Good evening, Peter.
Good evening, Brian. How are you? You got over that almond that you were choking on before?
That was only in the practice session, Peter. And,
what stage of the session?
And we're all smooth and sorted now.
All right, cool.
So Peter Fox, who isn't chewing on almonds at the moment, works for Texas Instruments Australia, and as you see, he provides most of the wonderful content that you see on the website, which I'm hoping that you visit frequently, because there's always more and more being added to it, with its particularly helpful, downloadable curriculum activities. So without further ado, I will just hand over to Peter, but quickly, my name's Brian Lannon, I'm your host for the evening. So Peter, we'll swing over to you. Or have you been chewing on almonds while I introduce you?
No, I think I'm good, thanks, Brian. As long as it's not one of the ones that used to be chocolate-coated. There's always that joke, isn't there, about sharing the almonds, and yeah, why don't you want any of these almonds? Oh, I only like the chocolate part.
Yes. I think I do recall that one.
Yeah, okay, probably for another time. All right, so let's have a look at what we'll hopefully get through in this session. We're going to look at transformations, obviously, as the topic suggests, but we'll look at reflections, which are done at a range of year levels. We'll start with some really simple stuff that you can do at year 7, but teach you some very important concepts, as well as covering some of the national curriculum. We'll have a look at translations and dilations, and finally rotations. Not sure if we'll get to rotations, but I've got a little file that I can demonstrate. We'll see how we go for time. So first one we're going to have a look at is something called handy reflections, and it's essentially looking at the students trace around their hand, and they just trace either their right hand or their left hand. In this case, it's the right hand one that's been done. And when they've traced it, they get a line drawing like this. The tracing in the activity, which is available from the website, has a grid on it. So the kids then plot a series of points. It's a bit like doing a connected dot plot, but in reverse. They start with the line and add the points to it. Then they estimate the coordinates of those points and do it as a connected scatter plot. So that's straight out of the Australian curriculum that we're going to do here is reflection in the axes. The students also can do some rotations. So let's have a look on the calculator to see what that one looks like. So here's the data that the student or students might have generated for themselves. They've plotted these points on the drawing of their hand, and then they get something that looks like that. Well, when they first draw it, they don't. When they first draw it, it's probably going to look a bit more ugly like that. So if the points are not connected, the first thing they need to do is change it. The instructions are in the activity, and they connect the points, and just to make it look a little bit neater, they do really tiny points, so it looks a bit more like a smooth hand. The amount of points they create is up to the student. So our first task in the activity has the students doing a reflection in the y-axis, unless, of course, they want to trace their left hand. That's going to take a lot longer. So I can give these new points a new name. As you can see, I've probably done this a couple of times. That's why I've had to put all those extra P's in there. And we can generate them. We could type them in one at a time. That would be silly. We can type a formula that just says, make it the negative of all the x values. So a reflection in the y-axis just makes all our x values negative. Handy to know when the students get to senior maths that they can do things like f of negative x. So I've created a new set of points. I'll need to go in and add them with a scatter plot. And you'll see I've done this with a number of activities in terms of reflections and rotations and so on. We can keep the same y points. And there's the points for our reflected hand. We'll do as we did before. We'll change them into connected points, and we'll just make the points a little bit smaller so it doesn't look as though there's some sort of a acne or wart breakout on the hand. And there it is. And of course, the activity then has them doing a reflection in the x-axis, double reflections, and they even swap the x and y values around to create a reflection in the line y equals x. They're just not aware of the fact that they're doing an inverse. So that's a nice, easy activity, and it shows that even at year 7, you can start doing some of these sorts of translations with the calculator.
Peter, just a question on that. Would that necessarily make you ambidextrous?
Well, it depends on how many hands they want to have. Yeah. All right, here's another one. Now, do you remember this one, Brian?
Yes, indeed I do. And I remember seeing a very neat little video of it that somebody put on YouTube.
Do you remember what year it was?
I'm going to go, well, it was 1970 when the dodecahedral 50-cent coins came out.
But for
that exam question, I'm going to go 2015.
You are spot on, sir. In further maths, PCE mathematics in Victoria, they asked this question of students, and apparently some of them were stumped. So I'll go back to our calculator. I'll start a new document just to make easy for people to follow. And this one could be easily done in the geometry application. So we'll get to see how easy it is to make that dodecahedron to start with. So it's a shape, obviously, and hopefully they're regular. And then we create the center of the shape, and as you move out, you'll see it says 16. That indicates that the default regular polygon it's going to create has got 16 sides. If you, however, move in a clockwise direction, you'll see that we can reduce or increase a number of sides from there. Ours has got 12 sides. So there's our 50-cent piece. We can then drag any of the vertices around to make it larger or smaller. I'll leave it like that. That should give us enough room. And now we'll take our first look at the transformations menu. I'm in the geometry application, as I said earlier on, and if I hover over that transformation menu, you can see we've got a couple of options. The one I'm going to choose, because we're talking about reflections, is number 2. And I can reflect this polygon, so I'm telling it what I want to reflect, and I can reflect it in any side just to make it easier for people. I'll do that one. And now we have the diagram as it appeared on the exam, minus the annotations on the coin. And next thing we'd want to do is measure an angle. And that's it. That was the answer to the question. Now, I sort of paused and gave some description as I went, but it took less than a minute. That's not bad for a multiple choice question, done and dusted. As long as the students knew how to use the transformation tool on the calculator, that was an easy question for them.
Less than a minute,
so I think. For option D, I think. I haven't checked. I don't suppose you know how many people got that right on the exam, do you, Brian?
I remember it was a minority. It was one that baffled people.
Yeah, which is a bit of a worry when you see how easy that was if they know how to use some of the geometry tools, particularly the transformations one. Now, the next one that we bring to mind, if we're looking at reflections and our senior maths courses in most areas, then we'd have inverse functions where we can get a reflection in the line y equals x just to create an inverse. And they end up looking something like that. So let's see how we can create that something. I'll get rid of my 50-cent piece problem, and we'll create a new one. This time we'll go into the graph application, and I'll just show you that we do have the geometry tools available for us in here, and you'll see there's the transformation menu, which has all the same options once again because it's importing the geometry characteristics. So let's start with a really simple function, x squared. Now, I do know that we can do relational graphing on here, and I know some of the people that are watching it probably say, well then why wouldn't you just go down and do a relation and swap them around and say x equals f1 of y and graph it that way. And yes, that would give us the result that we're looking for, but I want to do it as a reflection. So first thing I'll need to do is create the line in which we're going to do the reflection. That would be the line y equals x. Now, here's the catch. The trick to doing this one as a reflection is that you cannot do a reflection in a function. The calculator doesn't know that this is a linear function, otherwise we'd be happy to do the reflection. It only works with straight mirrors, plane mirrors. So the first trick is to draw a line on top of the line that we already have. I know that seems a bit weird, but I've drawn a line on top of a line. I'm just going to hide those points to neaten up my drawing. And we can't actually reflect an entire function, but we can reflect a point. So that's, I guess, trick number 2 to learn how to do this. So I'm going to put a point on this graph. There it is there. And I'm going to leave those coordinates there because they're actually pretty useful to have. Now, we're ready to do our transformation geometry. Transformation, which, by the way, is what the tree said to the bush, Brian. Geometry.
Yeah, okay. Moving right along.
All right. So we'll reflect this point in this line. So now, as I move this point, we can see its reflection. I can change the color of my reflection just to make it a little bit more obvious. Let's make it green, shall we? Hopefully that'll appear all right on people's screens. So here's the green point, our reflected point. We can draw a line segment through here and show that that's at right angles to the mirror for those physics types out there. It's another little reinforcement of the fact that we're doing a reflection in that line. But we'd like to leave a trail. Now we could leave just a geometry trail. There's a special name if we want that to this one over here. It's called a locus. So we can use this point to create a locus over here. And now we have our reflected function, and we know it's a reflected function because we reflected that point, and that point moves nicely along our inverse function. Now is the point where I think it would be good to say, let's have a look at those coordinates. That's where I would revert back to what I showed earlier. Once the students can see that the x and y coordinates are simply swapped around, that's when I'd say, oh, so the y and x have been swapped. Let's see if I could do that by defining the function as x equals f of y. So hopefully people can see why I'd start this way rather than just, oh, you just swap x and y. They can see it as they move the point. They can see what's happening to the coordinates. They've been swapped around. That's a nice little activity for senior maths classes to get into. So let's have a look at some sorts of questions that involve reflections. And this one applies to what we've just done. Given f of x is a quadratic function and its inverse, how many solutions are possible if we want them to intersect? Well, let's go back and have a look. The example that I've created here has 2 points of intersection, and both of them occur on the line y equals x. Now, I'll put my mouse over the origin, and you may see it pops up and says locus curve. I don't want to move, well, I can't move the locus curve, but you'll also see it says tab. When I press tab, it says, do you want to use the line? No. Press it again. Do I want F2 of X? No. I want the original one, F1 of X. Now it's, and I've just been pressing the tab key, folks. So now I can actually pick up my graph and move it. So here's the situation where we have no points of intersection. I think most people would agree that it would be possible to have just one point of intersection where the two graphs just touch on the line y equals x or kiss the line y equals x. So 0 points of intersection, 1 point of intersection. So grab that vertex again. And now I have 2 points of intersection. Now I have 4 points of intersection. Now, 2 of those points are on the line y equals x. The other 2 points that I have here, if we knew the coordinates of that point, obviously we'd know the coordinates of that point, which leads us to our actual big question. Is it possible to have 3 points of intersection? Now, it might not be obvious from the algebra, but hopefully it's obvious from the geometry right now, is that if I get 2 points of intersection, they're along the line y equals x, 4 points of intersection. We can see in this case that x-intercept and the y-intercept. So it seems impossible to get 3, even though it's not always clear from the algebra. Nice example of where the geometry can give us a quick answer. One more question for senior math students. This one's a little bit trickier. And this one we're looking at a exponential function. Same sort of question, only we're dilating our standard exponential, if you like, in such a way that its inverse, which we would know as a log, just touches at exactly 1 point. So f of x equals f negative 1 of x. That has one solution exactly. Now, I'm not going to solve that here. That's one for people to trial for themselves. It's a challenging question, but the thing I like about it is if you just wrote a to the power of x equals natural log, the log base a of x, and try and solve it, you can't just type in solve. It doesn't work because the calculator doesn't know you only want one solution. You need to have in the extra information that's important, and there's many ways you can do that. So that's our reflections. Now, do we have any questions, Brian, from any of the people in the chat space there?
The only thing that some people were commenting on was the strange, or shall I say, different appearance of your calculator screen there.
Oh, yes, it's morphed into the new one.
That is correct, yes. So both the keypad and the display, yeah, I think it's smoother. It's smoother than we've seen before. That's due to the new operating system, 5.0, and I've typed in a couple of links there if people want to follow those to update their own technology.
That's a very good observation by someone, because hopefully they will have also received information about how to upgrade their teacher software as well. So they can upgrade their teacher software. They should have received an email. If they're using a network license, it was probably the network administrator that's received that email, and they can do an upgrade to this premium version. Quick plug for the premium version for all those teachers using teacher software. When you install it, go up to the window menu, and you'll see mine says disable navigator. I don't want to do that. But they will have the option to enable navigator. So in other words, the navigator software is now built into the teacher software. So if your school's got a navigator system and you've all got teacher software, then you can now all use navigator, which I think is pretty cool.
Yeah, without the need for a separate piece of software.
Correct.
Yep.
All right, so, and there'll be more about that later on during the year as we do a special webinar on what's new in that software. You're kind of getting a sneak peek here anyway. But hopefully people also realise that these menus look very familiar anyway. They're all pretty much the same.
Yep. So
right,
just to
so
clarify, everything you're showing here tonight can still be done in 4.5?
Yes, in fact, the documents are opened. We're on 4.5, and the documents that I save will also work on 4.5. Unless you use one of the new features, then those files will open up just fine on 4.5. All right, so the next one we're going to have a look at is translations, and we'll do this with a geometry application, the same as we started off with the reflections. We looked at some geometry type stuff in the form of a hand. So let's just start up a new document. I can get rid of that one. And we'll go into a geometry application. Did I mention what the bush said to the... No, I'm just kidding. All right, so let's create a triangle.
I'm just wondering though, Peter, could we make that the keypad a little larger, perhaps?
No, that's the one thing I've asked the US team to change, because you can see it's kind of longer than what it was before. And I said, I want the keypad back to the same size as what we had before, because it's filled the screen from top to bottom. So they're going to chop out a little bit down here and chop out a little bit in the middle and maybe chop off a bit at the top so it reverts back to the same size as the original one. I agree, it could be a little bit big. All right, so I've created a triangle. And the next thing I'm going to do, if I'm going to create some sort of a translation, I need to give it an indication of where it's going to. You can even see from the little icon on translation, it's got like a little vector pointing or showing in a direction. So if I go on to points and lines, you can see I can create a vector. Oops. So there's my vector. And now I'll do my transformation. Translation this time. Now I could just translate a point. You'll see it'll be happy if I click on a point. It's also happy if I click on a shape. And I tell it to translate that shape using this vector. Now I'm going to change the color of that one just so that we can see which one's which easily. And I'll show you another trick shortly as well with regards to naming the points, which is also quite good. So if I change the length of the vector or the direction. But here's the bit that I think is cool. If I pick that vector up, kind of like it's gone to sleep, well, nothing's happening. Well, in relation to the vector, its direction is not changing, nor is its magnitude. So it's a lovely little lesson you can be having in Year 9, is to say, look, it doesn't matter where you put that vector. What matters is its length and its direction. So I think that's kind of cool that we can teach students that. And you'll see I can grab any of the things. The thing I can't grab, of course, is this, because that's controlled by our vector. Now, some of the things that the students should know if we're doing translations, let's have a look. We'll take some measurements. We'll measure a length along here, and we can measure the corresponding length here and see that they're the same. So we get the idea that length is conserved when we're doing a translation. Let's check some other measurements, such as angle. Measure this angle down here, and we'll measure this one in here. And we see the same thing. In fact, obviously we can say the two triangles are congruent, but the translation is not affecting the form of our original object. So that's important for when the students are doing it with functions as well. Next one, we can put that, if we wanted to, on the Cartesian plane. So let me just drop in a graph application, and some people may not have used this one. This is the grid. So you can actually show a grid, and I'm going to use a dot grid. And if I keep my scale on the X and Y axis as 1, that means I can go in nice whole number increments. Oops. Just don't move it around. So let's draw the shape again. We'll keep it simple. We'll do a triangle. Oh, I'm going to undo that. Another little thing I want to show people is under the settings, you've got a whole extra bunch of features in here. Automatically label points is kind of cool. So, oops, I did that same thing again.
Okay, so we don't need the points and coordinates command as we'd previously used.
Well, no, we can. But what I'm going to do is, let me just put that grid back on. Not sure why the grid went off. I don't believe I unselected that. So now let me try drawing my shape. So it's labelled my triangle ABC, labelled it automatically for me. I'll now create my little vector. And you notice if I hover over one of the grid points, it says point on. That allows me to do things like have it nicely horizontal, for example, or off on a 45-degree angle. And go in increments.
On meaning snap to grid.
Yes, yes, good point. Yes, snap to grid. Now let's see what happens when we do our transformation now. So we'll go back into the transformation tools, and we'll use translation. We'll do a translation of this triangle using this vector. Notice the way it's labelled the points. So
yeah, with A prime.
B prime. Yeah, I think that's pretty cool. So then the next question we might ask students is, and obviously you can check the coordinates of these things as well. I might just do that before we go ahead. We can see that's 1 across and 3 up. And then we can get the students to have a look at the coordinates of each of these points as well. So there's my first coordinate. And here's its corresponding coordinate. That is 1 across in the X direction and 3 up in the Y direction. I can make it 2 in the Y direction, or 1 in both directions, X and Y, or just in the X direction, or just in the Y direction. There's a few nice lessons that students can learn from this, almost talking about your IJK system for representing a vector, isn't it?
Yeah, or at least IJ.
Well, in this case, yeah. I'm not even going to try this in 3 dimensions. Maybe one of the viewers can try that one. I haven't tried that myself.
I'm sure it would work. Yeah, based on what you're showing us, I'm sure it would work in 3D.
It would be interesting.
Challenge for someone. Yeah.
Now, sorry about the jumping around of the mouse, folks, because I'm juggling the phone and the computer with one. Lesson number 2, get a mouse, right? So now I've got a second vector, and I can say, let's do another transformation. Do a translation again, but we'll pick the triangle that's already been translated by our first vector. So we can see, and you'll notice the way it's been labelled as a double prime because it's been, or it's under 2 transformations. And then, of course, we could discuss whether or not the order of those translations matters at all. So there's some nice geometry that you can get from that. Now, the one that, if people didn't see it earlier on this afternoon, was related to exponential functions. And if we have a look at something like this, this is an activity you can download from the Australian website. We can see this transformation is a translation. Every point on the function has been moved by exactly the same amount. Not obvious when you actually see the graph, but once you start putting points on it, these line segments, students can see that every single one of those is the same quantity. So we're reinforcing what you can do with the geometry. In fact, you could put the triangle on the actual exponential function and see it's going to do the same thing, and they will go to the corresponding points on the other function. So that's our translations. Dilations. Dilations are always fun. You see this sort of thing quite often, away from the x-axis. Is that the same as parallel to the y-axis? And students go, I'm not even sure what a dilation is now. I'm kind of confused. And it's interesting because the language that people use in some regions is different. In Victoria, for example, we often hear the expression as a dilation towards an axis or away from an axis. So let me just jump back on this exponential activity. If I'm having a look at this one here, I can swap and have a look. Is this graph compared to the original one, 2 to the x, 6 to the x, what's happening? We've got a line going this way and a line going that way. Kind of confusing, they're going in different directions. But if I talk about it as a parallel to the x-axis or towards the y-axis, we can see that all points are doing the same thing. They're all pointing towards the y-axis. Compare that with that one, where they're going in opposite directions. So we're trying to provide some visual clues to students. All right, so let's have a look how we do a dilation with a shape, and then we'll add that shape to a graph. That was my translation. Don't want that anymore. We'll start on the geometry application again, because these are the things you can be doing with students in the junior levels, and they have great repercussions for students in the senior levels. So there's my triangle, and let's try we'll do a vector again. No, we won't. I'm going to type a number just to be different. Two. So all I did there was just added some text to the screen, that text being a numerical quantity. So now have a look at the transformation. We'll do the dilation down the bottom there. We'll do a dilation of the triangle by a factor of 2 about some point. Let's do it about point A. Now I can change my original triangle down here a bit. I could change that quantity. People would probably realize you could attach that to a slider if you wanted to. And now if we're thinking about the sorts of things that students should be doing, similar triangles. And how do we know that they're similar triangles? And what's our scale factor? Well, it's dilation. So let's see what happens if I apply this same idea to the Cartesian plane. So we'll put in a graph application. I'll type y equals x squared. Drag my label out the way. I'm going to apply some geometry to this. This is one of the really powerful things about this environment. So, shape, triangle. So I'm trying to use the same concept as the students have had already. I probably should have got rid of the automatic labels there, but that'll do. So I've got 3 points. I've placed all 3 of them on the actual function itself, A, B, and C, and then we can create a dilation exactly the same as what I did before. So I can put some text on the screen. Now on the computer, you can right-click on your mouse. On the computer, you can do a control menu, or you can use the menus themselves to add text. I think it's under Actions. I'll type the number 2 again, so I'm doing exactly the same as I did in the geometry space. You can see I can still get the same geometry menu, transformation, dilation of this shape, triangle, by a factor of 2. Let's do it about the origin, shall we? Now, of course, I can just drag these points back down again, as I did before. Then we're going to ask ourselves, what would be the equation to the parabola that would pass through those points? Remembering those points are all points on the parabola because I put my triangle so that it existed on the parabola. Let's try it. I think most students would probably say multiply it by 2. But we can see, no, it's a half. And that's where we start discussing why is it a half and so on. I think that's kind of a cool way to show that the dilations that we're talking about for our functions are the same as the dilations, transformations, if you like, that we deal with when we're talking about shapes. So they're not 2 different concepts. We're trying to connect what they've learned earlier, prior learning stuff. All right, now, in our description, also said we'd deal with some matrices, so some transformations of matrices. So there's a little bit more work in this. I'm just checking the time. I think we're good. Now, I'll create a new document so that people can follow along. And I'm going to put a graph application in here. And we could do a function. We'll do a function in the last minute, but let's do a shape to start off with. I'll put the grid back on. You saw that I did that before, just so I can get nice whole numbers, dots. Then we'll put our triangle in. And I'm going to get the coordinates of our points. There's A and B. And C. Now, the next step is I need to be able to reference those coordinates. So I need to be able to store them somewhere. So I'm going to store that one as, let's call it XA. So it's an X coordinate of point A, and I'll store this one as YA. So it's the Y coordinate of point A. If you hover back over them, it'll actually tell you linked to YA, YA, and linked to, I'm not even going to try and pronounce that, XA. And then we'll do the same to this one. And because I did them in order, I know that this one's the XB. Oops. And I'll know that this one, store that in the YB.
That's a clever idea. I think I know where all this is headed, Peter.
Oh, do you?
I do, because I watched Stephen Crouch's webinar on data capture last week.
Yeah.
And when you were building these before, I was thinking, hey, that would be a good trick to do.
Yes. So we can see, got the coordinates all with logical names on them. Now I'm going to put in what's called a notes application, an amazingly powerful tool on this little device. And I'm going to put in a math box. insert math box. You'll see it says Control-M, which is what I'm going to use for all future math boxes. And I'm going to define my transformation matrix equal to, and I could pick up a template, but because I'm on the computer, I'm just going to type it in directly. 1, 0, colon, 0, 1. It's pretty much a do-nothing matrix. We can always go back in it. Let's do that now. I'll put in a negative sign just to make it do something. Next thing I'm going to do is, I'll call it T for triangle. I could call it T for transformation. Anyway, now I'll have my AX there. Oops, I think I'll call it XA. I did. There it goes. It's bold. I really like that it gives you the bold to remind you. The YA. So that's my first row. My second row is going to be XB and YB. And the next row is going to be that one and that one. Now, of course, we'd want to do some sort of a transformation. So we'll do that. P is going to equal T times M. So I've now got all the new points. And of course, if I change any of these values, being math boxes, everything updates, which is kind of cool. So now all I need to be able to do is refer to these points. It'd be really nice if I could plot them. Well, I can do that too. I'm going to call the new points XP, and I'm going to say that that is equal to a list that consists of, and the first one is located there. And the second one, so this is in matrix P, is going to be, I think this is a second row, first column. Let's see if I've got this around the right way from memory. And third row, first column. And you can see that my list of X points is 1, 4, and 7. And my list of Y points is going to be all the other ones. So we want matrix P, and we want, what do we want? 1, 2. And brain's now starting to, thank you, 2, 2. Thanks, Brian. Glad you're watching. And then the third one will therefore be 2, 3. Nope. What did I do? Oh, quit. I got it wrong. You didn't warn me. 3, 2. I'm back
3, 2.
Yeah. Dyslexic. There we go. All right. So now I can actually plot those points, the XP and the YP. I'll plot that as a connected scatter plot. So let's go into our graph and scatter plot XP and YP.
This is the cool bit. Yep.
Yeah, then we can just change that to a connected scatter plot. Now you can see I really need to just put those 2 points back together and add the extra one so I can get the entire triangle, because all I've done is a connected scatter plot, right? So it's gone point A, point B, point C. So I could add on one extra point, or you can, can't see, and just drop that extra line segment in, going from there to there. And the nice bit is it should move as I change it. Now, on my computer keyboard, I'm just going to press Control 4. What that does is merge this page with the next one, and I don't like that layout. I want one on the top and one on the bottom. I'm just going to change the proportion there. Now, what we need to be careful of here is the aspect ratio in our graph application is no longer square. Now, some of these points may disappear. I'm not particularly fussed about that. But let's do a zoom all the way down near the bottom here, as we have a zoom square. And there we go. Now, everything is dynamic, so when I change things, oops. Now, that is one thing you've got to watch out for. When you merge the 2 pages, you've got to go back and reactivate all your math boxes. I know I could have done activate all, but now we should be good to go. And you can see it's working same as what it did before. You may think, well, why did I bother? Well, that's because I can do things like that. Oh, there you go. My points didn't land on my scatter plot. I should fix that. Not right now, I won't. So you can see I can create the dilations, the transformations that, what do we want, a 2? Maybe a 1. So you can see that I can create these transformations. Now, I'm also looking at the time thinking, if I don't get a wriggle on, we'll miss out on the last 2. So the last 2, using a very, very similar approach, but this time I'm working algebraically, so I'm working with the function. So working with the function, we can set it up. I've got my matrix down here, my do nothing matrix, and we'll multiply it by its current x and y, and do nothing as far as translations are concerned. And here's one of the little tricks down here. So what I'm doing is storing this xp, let's call it my x point, some sort of x thing, and it says, as I did before, take the first value in that A matrix, first row, first column. So it's going to take the answer here, this answer over here, and it's going to use that. See how it's got an x? Now, to illustrate what that does, let me just change that up a bit. Let's change that to a 2. So you can see xp is just this expression here. And if I change this to a -1, you'll see down here, yp is now the expression that is put down here, which means you can actually graph this as a relation and do xp equals yp, and it will have your x's and y's on the respective sides of the equation. There's a little bit more work down here. Mine's doing a little solve, so it's trying to write it as a function. And what that means is, as you can see up here, is if I change these things about, it's actually rewriting my function at the top. So not just dealing with points anymore, we're dealing with the entire line. So I'm thinking I could put a negative sign in there. I could apply some sort of a dilation. And let's check to see how our transformation works. Translation is working also. So it's kind of nice that you can put all of those things in and see the function update, but it's using exactly the same concept as what I just did. Now, the agenda said rotations as well. Let's have a look at this one. This time I've created a slider called rotation. Well, I called it rot because rotation was defined and it was going to be too big. So I just called it rot, which makes it look really weird, but never mind. And this down here is a rotation matrix. So now I can just click on here and rotate my function, which I think is pretty cool. If I go back there, you'll see it actually picks up, oh look, you've just made the, swap the x's and y's around and reflect it at the same time. And I think it's kind of cool that we can just grab any function and rotate it around the axis. Now, is there an activity on that one? There sure is. On the specialist section of the Senior Curriculum Inspirations, there is a series of activities. Let me see if I've got that website up at the moment. On the Australian website, if you go into Senior Curriculum Inspirations, we'll go into the Victorian curriculum. I think it may be under Year 11 Specialist Maths. Let's just check. Here they are. Now these are some beautiful activities. The first one, Advanced String Graphs, is just stitching the X and Y coordinates together along to create a nice pattern, which turns out to be a quadratic function rotated through 45 degrees. The second one, Advanced String Graphs Part 2, that stitches points along the lines y equals x and y equal negative x. So you get very similar sort of a graph, but rotated through 45 degrees. So the student can actually get that quadratic function and rotate it through 45 degrees. And the algebra, believe it or not, turns out to be much easier when you do that compared to trying to do it by hand, as in coming up with that quadratic equation by hand. And the third one you can kind of see, let's just jump into it. You can kind of see from the actual image up there that it's rotating. So there's our function, and in this particular activity I've just used a slider there to rotate that set of straight lines around. And the other thing that's really cool about that is if the student wants to get the consecutive points of intersection between each line, they can do exactly the same. And that activity then goes into a little bit about the distance between the function, the focus, and the directrix if they want to prove that it's a parabola. Beyond the course, but as you can see, it says focus, directrix, equidistant, mapping. They're the sorts of vocab that it's using. So that's why it's an advanced activity. So I think we're almost out of time, Brian, and I think I've covered everything that was on our agenda.
Done very well. Yes, thank you very much, Peter. I've just been typing into the chat there the links to a lot of these activities. I know we mention it frequently, but I do hope people check the website and look at senior curriculum inspirations and Australian curriculum inspirations, because it's just such a wonderful resource of what's there, what's available for free download. So my screen's on share now. These are the ones that you were just showing us, Peter.
Yeah.
That's the Year 11. But senior curriculum inspirations, and as you can see, it's state by state. You just click on the teacher tab, and the other one, of course, is Australian curriculum inspired. Same sort of thing, year by year and topic by topic. Can I just, before I close this out, can I just draw attention to a couple of other things? On the front page of the website, so that's education.ti.com/en -AU, in other words, the Australian web page of Texas Instruments, or just Google Texas Instruments Australia. You can see here, this is where the link is for that upgrade for 5.0 for the latest operating system. And accompanying that will also be the later generation of handhelds. So that will they'll be available soon for purchase, or are they already, Peter?
Well, we're waiting on stock. I was just visiting some people up in Queensland recently, and had to take up engineering samples because the products are still being manufactured as we speak. The other thing I should mention too, the instructions for translation using matrices, because that can be quite tricky. I've written up a 4 or 5 page set of instructions with screenshots so that people can follow the video, or because that'll be on YouTube and that pause it and so on, or they can just follow it literally step by step. So that will be included in the stuff that comes out to everyone that's on board tonight, is those 2 sets of instructions for translations with matrices.
Terrific. And as always, if you've put your name down to look at this webinar event, you will automatically be receiving the links to all the documents that Peter has demonstrated tonight, and the matrices assistance that he's just mentioned. Just before we go, there's been some mention also of the curriculum inspiration webinar series. This is a new thing that we're just trying this year. They're only short 15-minute webinar events, and the idea being that when you download one of these activities, you have a short video to where the writer or another of our trainers talks you through how that activity works. So just a 15-minute overview. And we record those live. We send them out live in the time slot 4 to 4:15 in the afternoon, with the idea that if you wish, it's something that could perhaps be tied into an after-school staff meeting. So Curriculum Inspiration is the name of the series, and this afternoon, Chris Orison was showing us an activity that he wrote on exponential learning. Tomorrow evening, Peter Flynn will be taking us through a non-CAS version of the same thing. And next week, next Tuesday, we see Pythagoras is not real. Well, does that mean he's complex, or is he just imaginary? You'll have to wait and see if you want to tune into that one.
Very good. Very good.
Next thing, you'll be ruining the Easter Bunny and various other things, Foxy. I don't know.
Well, it does actually mention something about Easter Bunny and Father Christmas in the write-up to that. The other thing I noticed on the chat, someone wanted to know what's the answer to a to the power of x equals log base a of x. Well, I don't want to give it away too much, but the things you want to have a look at, you can identify that the fact that the x and y will be the same at the point where those two graphs just kiss each other, or you can also use the fact that the tangent to both functions at that point will equal 1, which of course is the gradient of the line y equals x where they're touching. So we can either work with the fact that the gradient is equal to 1 where they touch, or we can work with the fact that x and y have the same value because they intersect on the line y equals x. So that's my last clue. Otherwise, they can give us an email, Brian, and we can help them out as to how they might solve it. It's a good, challenging problem. I like it because you can't just type in solve.
Okay, so some homework there. Thanks, Peter. If there are any final last-minute questions that you'd like to put to Peter, now's your chance. I'm about to close the event, and when I do, you'll be taken to a page where we invite your feedback. And I've already mentioned the follow-up email that you will receive with links to the associated documents and also your participation certificate. If you'd like to watch the whole thing again, you can do so in that on-demand section of the webinars that I've just shown you, or also go to our YouTube channel. Of course, we're hoping that you're subscribing to the newsletter. If not, there's the link. If you do have any other questions at any time, the numbers are on your screen now. So thank you once again for joining us this evening, and a particular thank you to Peter, our presenter.
Thank you.
Good night. Good night to all.
And to all a good night.